Okay, since you all are so quiet, I think we can start this dissertation act. So I'm really delighted to welcome you all to this public defense of the doctoral dissertation of James Joyce. And the title of your dissertation is Environmental Considerations in the Zero Waste Valorisation of Bauxite Residue, a Life Cycle Perspective. And my name is Tove Malmqvist. I'm a colleague to James from the same department here at KTH. And I will work as the chair of this dissertation act. My role is to make sure everybody does what they're supposed to do at the right time, etc. So first of all, I'd like to introduce the main actors of this act. So of course we have the discussant, James Joyce, and he has written his PhD thesis in a subject called Planning and Decision Analysis with specialization in environmental strategic analysis. And you have been working here at KTH at the Division of Environmental Assessment and Management at the Department of Sustainable Development, Environmental Science and Engineering, and in short, we call it SEED. Okay, and we also have an opponent here. So you will examine and discuss James' dissertation, and it is Professor Stephanie Hellweg from the Institute of Environmental Engineering in the Department of Civil, Environmental and Geomatic Engineering at ETH in Zurich. We also have a grading committee, and the grading committee will evaluate and grade the dissertation. And the grading board consists of Professor Gregory Peters at the Department of Technology, Management and Economics at Chalmers University of Technology here in Sweden. We have Associate Professor Joachim Krook at the Department of Management and Engineering at the University of Linköping here in Sweden. And we also have Associate Professor Theodora Rettigan at the Department of Chemistry and Chemical Engineering at Chalmers University of Technology. We also have a replacement for the grading committee in case anyone should not have been coming, but you're all here. We are happy for that. But anyway, I'd like to introduce also Associate Professor Kerstin Forsberg, sitting over there, from the Department of Chemical Engineering here at KTH. Yes, and another important person is James' main supervisor, Associate Professor Anna Björklund, here, also from SEED at KTH. We also have one co-supervisor here, Professor Göran Finnveden, also from SEED, KTH. And we also have a co-supervisor in Leuven, Professor Karel van Akker in KU Leuven. Yes, and then we go to the procedure for this dissertation act. So James will now start to present and summarize your thesis. And after that, I will hand over the word to Stephanie, the opponent, who will discuss the thesis with James. And after that, it's time for the grading committee to pose their questions and give comments on the thesis. We never know how long this will take, but approximately 2 to 3 hours, usually, but we never really know. After the defense, then the grading board will meet to discuss and decide if the candidate will pass the examination. At this occasion, you may also invite the opponent and the main supervisors to join this meeting. And until the grading board comes back with a decision, we all who like to come together with us at our department. But I will give you further instructions about that afterwards. Okay, so now I hand over the word to you, James.
Thank you, Tuva, and thank you everybody for coming to this, the defense of my PhD thesis, Environmental Considerations in the Zero Waste Valorisation of Bauxite Residue, a Life Cycle Perspective. So, as Tuva mentioned, my first task today is to provide a brief overview of the research I've been doing over the last 3 to 4 years, and the plan is to convince you that a life cycle perspective is important when looking at the environmental implications of recycling and valorization processes. I'll also present to you a new life cycle impact assessment method for characterizing the impact of ionizing radiation from naturally occurring radioactive materials, and present some tools and approaches which I've developed to help streamline and simplify these assessment processes, so that a broader group as possible can take advantage of the valuable insights that they can offer. And I'll be doing this all through the medium of bauxite residue. So what is bauxite residue? Bauxite residue is a waste product of alumina refining, which is the first stage in the production of aluminium. Briefly, the bauxite enters a process called the bioprocess, where high pressure, high temperature sodium hydroxide is used to dissolve the aluminium-bearing minerals. These aluminium-bearing minerals are then sent off to produce aluminium. And all of the stuff that's left over, along with some of the caustic sodium hydroxide, ends up in the bauxite residue. This is a thick red mud with a pH of around sort of 9 to 13. A lot of this stuff is produced, about 150 million tons annually worldwide. And it's estimated that up to 4,000 million tons of it are stockpiled. It's also a growing problem. Demand for aluminium is such that it outstrips supply of recycled aluminium, which means that for decades to come, we're going to need to supplement this with production of primary aluminium. And where there's primary aluminium, there's bauxite residue, 3 tons of it for every 1 ton produced. Only 3% of bauxite residue is used for anything at the moment, which means that 97% of it ends up in places that look a bit like this. This is a bauxite residue disposal area where bauxite residue is stored close to alumina refineries. The problem is that some alumina refineries are starting to run out of space. One refinery I've spoken to estimates that they have 20 years left of storage area, after which they need something else to do with the bauxite residue in order to continue production. So, in order to help do something, contribute to the solution to this problem, the Red Mud project was set up, and my PhD forms a part of this project. This is a EU Horizon 2020 funded European training network consisting of 15 PhD students at 9 academic and industrial institutions around the European Union. The aim of the project is to develop zero waste, environmentally friendly valorization flow sheets for fresh and previously stockpiled bauxite residues. Valorization means literally to extract or realize value from something. And in the specific case of bauxite residue, we're talking about this targeted extraction of specific valuable materials. There are 3 main ways to do this. The first is to target the bulk constituents in terms of metals, which are iron and aluminium. The next takes advantage of the fact that when you remove the alumina from the bauxite, this serves to concentrate some of the trace substances within the bauxite ore into the residue. This includes titanium, rare earth elements, and scandium. Unfortunately, alongside these, the concentration effect also happens to naturally occurring radionuclides, which occur naturally in the bauxite ore. And so understanding what happens to these naturally occurring nuclides, which are known as norm, is an important aspect in bauxite residue valorization. Finally, the third approach is to use the bauxite residue for its bulk properties and use it to create cementitious binders, which may be either high iron content cements or something more exotic like inorganic polymers. My role in the project is to make sure that when the other researchers claim that they're doing something environmentally friendly, there is evidence to back this up. Valorisation, when viewed in isolation, is often assumed to be environmentally friendly. The logic seems to go, waste is bad, therefore doing something with waste is inherently good. But this isn't always the case. Valorisation processes will require energy and materials, which have an upstream environmental impact through their production and generation. In addition, the use of valorized products will potentially have environmental impacts in the use phase or due to their final disposal. On top of this, the use of valorized products may displace the production of conventional products elsewhere in the economy, and there may be environmental benefits associated with this. So it's vital when we're talking about the environmental implications of valorization technologies that we take a life cycle perspective. Luckily, there is an internationally recognized and standardized quantitative methodology to do just that, to look at the life cycle environmental impact of products and processes. This is called life cycle assessment, which is abbreviated to LCA, and it's the most important method that I've used in my thesis. A thesis which consists of 6 papers and answers 4 specific research questions. The first of these research questions concerns naturally occurring radioactive materials and their incorporation into the life cycle assessment framework, and is covered by papers 1 and 2. Research question 2 deals with modeling approaches for early stage development of new technologies, and is covered by papers 3 and 4. Research questions 3 and 4 are more specific to bauxite residue. The first of these asks about identifying hotspots in a simple valorization process for a single step, while the second research question 4 deals at a higher level with full system-wide valorization flow sheets with multiple targets. So, to the results, starting with research question 1, can and should the enhanced exposure to naturally occurring radioactive materials resulting from industrial processes be integrated into the life cycle assessment framework? In paper 1, we set out a framework for developing a new life cycle impact assessment method for norm exposure, and in paper 2, we implemented this framework as a new characterization method. In order to understand the environmental impact that is caused by norm, we need to be able to quantify the causal relationship between its exchanges between norm and the biosphere and the technosphere, and receptors such as humans or ecosystems. To do this, we used a source pathway receptor framework. The idea here is that in order for a substance which is potentially damaging to actually cause an impact, there needs to be a pathway between its release and a susceptible receptor. The bottom half of this diagram shows the exposure pathways as a result of releases of radionuclides to the environment, and their subsequent translocation and potential accumulation within food chains in order to, by various means, impact upon sensitive receptors. The top half shows a different exposure routes, which is the incorporation of radionuclides into products. And these products can then come into proximity with humans and cause a potential impact. In the second half of paper 2, we take this new life cycle impact assessment method out for a test drive by doing a theoretical case study on the disposal of bauxite residue by either using it in bricks or using it in ordinary Portland cement. The most interesting results of this case study came from the human health impact. We found that the use phase far outweighs the impact the impact of the use phase far outweighs the impact associated with environmental releases of nuclides. We also discovered, perhaps unsurprisingly, that incorporation of bauxite residue leads to increased ionizing radiation exposure due to the higher levels of radionuclides in this substance. This represents an instance of potential burden shifting, which is important. Burden shifting is when, by aiming to reduce impact in one area, for example, carbon footprint or acidification, you inadvertently increase impacts in some other area, in this case, ionizing radiation. And prior to our implementation of this new method, these impacts were going unassessed. We also discovered that the use phase impact from conventional building materials, so that's standard bricks and cement, also made a significant contribution to this impact. And in fact, when compared at an endpoint level with other environmental and impact categories which damage human health, can be the overriding impact. which once again serves to re-emphasize the point that this was a worthwhile endeavor. Moving swiftly on to research question number 2. This asks, what is the most suitable approach to modeling industrial scale life cycle impacts of bauxite residue valorization using lab scale data and in collaboration with non-LCA experts? Early on in the REDMUD project, it was very easy to get the other researchers to draw out unspecified flow diagrams of the processes that they wanted to implement. Unspecified in the sense that they knew roughly what processes they wanted to use, they knew roughly what inputs they would require to achieve these processes, but they weren't capable yet of putting any numbers on these different flows. As the project progressed and lab trials became up and running, we started to get experimental data which we could use to start putting some numbers onto these flows. This type of data lends itself to a particular type of streamlined predictive options appraisal LCA. It's possible to do this in conventional LCA software, such as SEMAPro, but those kinds of softwares aren't designed to do that type of assessment. An analogy I recently heard was it's like going to McDonald's for a salad. You can get a salad at McDonald's, but if you want a decent salad, it's better to go somewhere else. And that somewhere else in this context is this. This is LCOps, which is a piece of open source LCA foreground modeling software, which I developed as paper 3 in the thesis. The idea here is to mirror the experience that I just described in the previous slide. So on the left-hand side, you can see the interface where you can draw your unspecified flowchart using an interactive drag and drop system. And then you can start to build your parameter sets in a different screen. These are then combined to form an LCA model, which can then be sent off to the open source LCA calculation package Brightway 2, which returns the results of LCOps, and they can then be explored in an interactive and informative way. Most LCAs start with a drawing of a flow diagram, such as the one you can see on here, on a piece of paper. The next step, however, represents somewhat of a bottleneck, because then you have to turn this flowchart into a life cycle assessment model. Often this involves transcribing it into a series of linked tables, and this can both be time consuming and act as a barrier to non-LCA practitioners to do these kinds of assessments. It would be better if you could just take this photograph and get the computer to create the life cycle model for you, which is exactly what we do in paper 4. Paper 4 describes a computer vision pipeline for turning a process diagram into an LCA model. It's a series of algorithms that identify the boxes and links in these flow diagrams and sort them out into an LCA model which can be exported to LCOpt for analysis. Research question 3 asks about the major environmental considerations in the creation of inorganic polymers as a single-step valorization pathway for bauxite residue. The process that we assessed was developed by Tobias Hertel, one of the other PhD students in the REDMUD project at KU Leuven. And the idea is that you get some bauxite residue, you add a source of carbon and a source of silicon, and you place it in a rotary kiln to fire at somewhere between 1100 and 1400 degrees centigrade. What this yields is a chemically active precursor, which when you add an alkaline activating solution to it, starts a polymerization reaction, which eventually results in the formation of a solid block, which can be used in paving applications. So we took this information and we did a streamlined life cycle assessment in order to identify hotspots of environmental impact within this process. These are the results. This diagram can look a bit daunting at first glance and can be difficult to parse without explanation, but once explained, it does contain a lot of useful information. The idea is that it can be read as a hierarchical pie chart. So starting in the middle, each subsequent ring shows you the contribution of different levels of the process to the one preceding. What we can see here is that the precursor, this big green part, contributes the majority of the impact for the climate change category. At the next level of the chart, however, you can see this consists mostly of the fuels used to fire the rotary kiln, this blue section, but there's also a significant contribution from the direct emissions of carbon dioxide from the reaction of the carbon source with the iron in bauxite residue. There's also a secondary hotspot up here for the alkaline activating solution. A similar pattern to this was seen in a majority of the other impact categories. The one major divergence, however, was for resource depletion. And here, the activating solution represents the main hotspot of environmental impact. And while the precursor still represents a certain amount, it is the silica source rather than the fuels that are contributing this resource depletion impact. Hotspots of environmental impact represent opportunities for impact reduction. And from the analysis that we did, we were able to come up with some sensible and actionable recommendations. The first of these is to reduce the amount of precursor in the block mix. Some of these blocks were highly over-engineered for paving applications. They had compressive strength far in excess of what is required to be used as pavers. And subsequent research has now shown that with levels as high as 70% raw bauxite residue, mixed with 30% of the activated precursor that's gone through this firing, we can still end up with a block with a compressive strength more than suitable for use as a paving. In terms of reducing the impact of precursor firing, in the short term, a switch away from fuels like hard coal and heavy fuel oil to natural gas can offer environmental savings. But in the medium to long term, new technologies such as microwave furnaces powered by renewable energy can reduce this even further. There's also the option to look for alternative sources of alkali and potentially take advantage of the fact that bauxite residue itself is highly alkaline in nature. So finally, moving on to research question 4, which asks what additional life cycle considerations are required when we look at more complex multi-stage valorization pathways. As I described earlier, there are multiple targets for valorization of bauxite residue, and there are multiple routes that you could go down to extract one or more of these valuable materials. At the moment, however, there's a lack of quantitative data as to how these processes all link together and how these processes work, which means it's too early in most cases for even streamlined life cycle assessments. All is not lost, though, because we can use life cycle thinking to gain some useful insights into these processes. The most important aspect of this is the understanding of the idea of environmental balance. So when bauxite residue is sent to valorization, you no longer have to send it to landfill, so the impacts associated with landfilling it are avoided. Similarly, when you produce useful products from this bauxite residue, they have the ability to displace the need to produce similar products elsewhere and thereby avoid the environmental impact associated with that production. This avoided burden can be thought of as sort of an environmental credit. On the other side of this balance, however, you require energy and materials, and processes themselves can lead to environmental impacts. And when you're conducting your valorization processes, and these can be thought of as an environmental debt. The situation we want to end up in is where the amount of environmental credit isn't completely eroded by the environmental debt incurred through the use of your valorization process. In terms of assessing this, on the avoided side, we conducted something called a size of the prize analysis, and this looked at the composition of bauxite residue and the potential extraction of these materials, and looked at the maximum possible amount of environmental savings we can gain from displacing their companion materials. On the other side, on the debt side, we came up with an analysis called the red flags analysis. The idea here is that you're looking for things in the flow sheet which can have a disproportionately high environmental impact. In the case of bauxite residue, when we applied this methodology, we saw that direct emissions from chemical reactions, for example, the release of carbon dioxide from the decomposition of sodium carbonate or from the carbon source like we saw for the inorganic polymers, are important. Chemical synthesis is also important, particularly things like ionic liquids, which are highly specific solvents used for rare earth element extraction, which means that regenerating these solvents and using as little of them as possible is a very important aspect in these flow sheets. And finally, heat and mechanical energy for running these processes also can represent an environmental hotspot. In order to validate the inferences that we gained from these two prior analyses, we also did a streamlined LCA of a combined iron and inorganic polymer system. These did validate our assumptions from our 2 previous analyses, but also yielded some interesting conclusions of their own, particularly with regards to the need for synergy between valorisation routes. On this chart, you can see in red the environmental debts that we're incurring, the environmental impacts, and here we have the displacement. What we see is that neither of these bars, in fact none of these bars, are large enough in of themselves to cross over the y-axis into the region where you see an environmental benefit. And it's only by combining the extraction of iron and inorganic polymers that we get into the right side of the balance. So that almost brings me to the end. To conclude, I hope I've persuaded you that a life cycle perspective is important when considering valorization technologies, that norm is a potentially important impact to consider from a life cycle perspective, and that even quick and streamlined assessments of the environmental impact of these technologies can yield important conclusions and lead to important recommendations. Finally, the more people capable of doing the assessments, I think the better. So what does the future hold? Unfortunately, the REDMUD project hasn't overnight managed to solve the problem of bauxite residue in the 4 years that it's been in operation, but the future, I think, is bright. There is research continuing worldwide on this theme, and some very interesting and important new projects have been started here in Europe, including scaling up inorganic polymers production to pilot scale and fostering collaboration with industry, which is going to be vital if we're going to solve this problem. In my personal view, I think the way forward lies in tailored residue-specific, site-specific processes that make sense in the local context of the alumina refineries. And it's my hope that the library of knowledge presented in this thesis, alongside the tools and approaches that I've shown you, can make some contribution to ensuring that the future management of one of the world's most abundant and important industrial wastes is carried out in a more environmentally sustainable manner. Thank you very much.
Thank you very much, James, for this wonderful introduction and summary to your thesis. Okay, so now it's time for the opponent, Professor Hellbeck. And I think it would be nice if you sit here together. And I hope you can use this microphone as well.
Well, first of all, congratulations to your thesis. I really enjoyed reading it. I must say, when I read the title, I wasn't expecting what I then read. I think you had a much broader overview and much more overarching than I expected. I wasn't expecting to read anything about image recognition, about new LCIA methods. And I was really surprised, positively surprised, I must say. So I was impressed. I learned a lot, and I think overall this is a great piece of work. I would like to ask you some general questions, but especially I will also focus on some specific questions because in general I think I was really happy with everything you did. So the first very, very overall question is, you showed us what you did, and this is a lot. What are you most proud of?
What am I most proud of? That's an interesting question. Sorry, can you hear me? That's a great question. To be honest, I'm most proud of something that didn't come up in the presentation, which is fostering the idea of life cycle perspectives and life cycle assessment in the other researchers in the REDMUD projects. I'm hoping that they'll be able to take what they've learned from the brief training courses we did here in Stockholm, and also from my constant pestering of them to take this forward and hopefully apply this usefully when they go on to develop new technologies in the future.
Okay. So the practical side a little bit. I will come to that later also, because I think, with the software you have done a big practical piece of work, which can help. So maybe I start my questions nevertheless with in the sequence of your PhD thesis, and then I'll come to that part also later. So you developed this radiation LCIA. I'm not an expert in radiation, but I heard there are others, so I'm really happy that you also get some questions afterwards. But I'm an expert in LCIA methods, and I try to ask my questions in that regard. So you suggest to have a separate midpoint impact category for the norm ionizing radiation category.
Yes.
And I was wondering, why do you want to have it separate? Why don't you want to merge it with the existing ionizing radiation category?
The main reason it's kept separate is because the previous ionizing radiation category deals primarily with artificial radionuclide releases from the nuclear fuel cycle. And so the fate and the transport models that they use are more suitable for that specific, those specific conditions. For norm radionuclides, they can be emitted from anything from phosphate mining to coal power production to bauxite residue valorisation. And so a more general fate model was required in order to assess the transport of these in the environment. And so there was no way to harmonise the two sufficiently, in my view, to justify merging them as a single impact category.
Would you think this is necessary to put it in one impact category, to harmonize exactly all the models and so on? If you just think of other impact categories like toxicity, would you expect them to all come from, if you look at different toxic emissions?
It's like you say, that in use tox there's a separate category for cancer and non-cancer, carcinogenic and non-carcinogenic emissions. So I don't think it's too much of a problem to keep the two separate. And in some ways, that level of disaggregation may allow you to make more interesting conclusions rather than just looking at a single number for ionizing radiation. You can identify whether the impact is coming from a reliance on nuclear energy, which may be important in some countries. I know Sweden has a lot of nuclear in their mix, and France especially does. And so splitting that out from the impact of naturally occurring radionuclides, I think, might be particularly useful.
I understand what you're saying, that it's interesting to separate where it's coming from, but I wonder whether you could not also do this if you have one category. And you're saying that, cancerous and non-cancerous emissions, I agree absolutely, these are two different effects, but in the end you're looking at the same effect here, right, for the radiation category?
Yes, that is true. That is true. Yeah, I mean, it is possible. There is a conversion you can do to turn the original ionizing radiation category from the units they use of kilobecquerels of uranium-238 equivalent into man-sieverts, and then you could have the same midpoint unit. So it is certainly possible to do.
Yeah, and just because, we already have 12 now.
Yes, absolutely.
And that would be a next question. Well, maybe I put this a little bit later, but in your case studies you had all the 12 indicators, and now 13 indicators. And yeah. But I understand what you're saying, that you would like to kind of separately also look at what the contribution is. That is certainly of value. You didn't mention the term uncertainty, but it didn't then see much discussion of that in your work. Maybe you can elaborate a bit of what you think are the biggest uncertainties in your method, and what would you recommend in the future to consider those?
Sure. Yes, uncertainty analysis is a very broad area, but the main types of uncertainty in there are parameter uncertainty, which surrounds the parameters that we've used to describe the characteristics of the radionuclides and various other things within the model, which is an important first type of uncertainty. Then there's modeling uncertainty around the choice of models that we've used and the way that they all fit together. And then additionally, there's decision rule uncertainty around some of the assumptions that we've made and the choices that we've taken in terms of stuff like the redistribution of daughter radionuclides and the inclusion of the full impact of the radioactive decay chain. It wasn't possible to quantitatively assess this uncertainty. A lot of the parameters are just a single value that we could find. There was no ranges that we could to plug into something like a Monte Carlo analysis. And so it's dealt with more qualitatively and perhaps too briefly in the thesis itself.
So do you have a feeling of what could be the dominating source of uncertainty? Because I assume you have, as you say, you now say parameter uncertainty, but you have parameter uncertainty everywhere, right? So variability between the different red muds, I guess, they are not all the same, and then you continue with the impact assessment. Do you have already a feeling, or
it's
is this really something to leave for the future?
It's maybe something for the future. There is certainly decision rule uncertainty surrounding some of the ecosystem results that are particularly affected by stuff like daughter nuclide redistribution. My hope or my inference is that the uncertainties that we have introduced in the characterization model are systematic uncertainties. So as long as you're only using it for an internal comparison, everything is affected in the same direction, so that the results and the inferences that you can take from it are still valid, even if the exact number isn't exactly correct.
Yeah. So what would you do as a next step if now you had more time to go into this? How would you proceed to get this inside your methodology?
That's a very good question. Oh, me. Sorry. Is this better? Excellent. What would I do next? That is a very good question. I guess the best thing to do, if there was the time to do it, would be to go out and collect better data for the parameter uncertainty side of things. Some of the assumptions we made were assumptions, particularly around potassium emissions. And so if I had unlimited resources, I would go out and collect those, or develop those conversion coefficients and the other types of parameters that are required for the fate modeling for these radionuclides. As a more sensible option, I think looking into the issue of the subsequent distribution and toxicity of degradation products, both in terms of the transmutation of radionuclides, but maybe also extending that out to chemical degradation, would be an interesting addition to these types of impact assessment methods.
You also mentioned the model uncertainty, which certainly is also another one. How would you approach that?
That's a good question. It's a long time since I looked at these models in detail.
Yeah.
A lot of the models that we've used, we sort of created a meta model by taking existing models and sort of adapting them and bolting them together. So some of the model uncertainty remains inherent to those original models, and I wouldn't feel comfortable trying to make USTOX any better than it already is. And a lot of the radiological models would require someone with a bit more radiological expertise than me to improve. So I'm afraid I don't know the answer to that question.
No,
right
well,
now.
I mean, you did a very good first step. Of course, you cannot do everything. And this is a difficult question, always, yeah. One of the choices that they made was about the landfills, and this is now a detailed question. It wasn't that relevant, so it's not that important to look into this, but I was wondering how you did it, because you assumed, I think, the long term, you assumed this 100% leakage, and then for the short term, I think you assumed constant leakage throughout the 60,000 years?
Yes, that's right. It is undoubtedly a limiting assumption, and again would be one of the things that would be top of the list to go and assess if it turned out that it was an important thing to look at from a life cycle perspective. But essentially, the way the eco-invent model long-term emissions is to take the short-term emissions over 100 years, and then sort of extrapolate this out to 60,000 years to figure out how mobile or immobile a substance is in landfill. Because we didn't have the short-term point on this line, we started with a worst-case assumption of the long-term point on this line, that as the clock ticks around to 60,000 years, the very final atom of these radionuclides leaches out into the groundwater surrounding the landfill, and simply linearly extrapolated back to 100 to work out something which we could use as a limiting assumption for short-term emissions.
Yeah. So do you think that could be improved? I mean, for the short-term emissions, at least for the other emissions, those were mainly based on measurements.
Yes, that certainly could be improved.
So that would be a next step then to tackle that. No?
Definitely.
You also assessed workers' exposure on the landfills, and also that was not important. So I understand if this is not the focus of your work, because I mean this apparently wasn't something showing up. But I still wondered how you did this.
Yes.
Did you use the short term or the long term here, or how did you deal with that?
This was based on external exposure. So the idea was that workers spend around 150 hours a year dealing with operations on the landfill site. And they're generally only exposed to the top layer of the bauxite residue because as you pile this up, the bauxite residue on top has a shielding effect from the gamma radiation that is released by the bauxite residue further down in the landfill. And because we were looking at it from a kilogram of bauxite residue's point of view rather than a worker's point of view, this kilogram down here at first is emitting gamma radiation all over the place and impacting upon the workers that are milling around it. But as the bauxite residue landfill fills up, this particular piece of bauxite residue is becoming more and more shielded, and that's why the chart drops off quite steeply in terms of the impact that this residual piece of bauxite residue is having on the workers. And so we used a shielding model and derived some assumptions based on the operation of a landfill at the Aluminium of Greece refinery in order to estimate the potential workers' exposure.
But this was during a time, what was your time frame there?
The time frame was integrated out to infinity, if I remember correctly.
All right,
but
okay.
Pretty soon after you start having a shielding effect by ramping stuff up, the levels of exposure drop to negligible levels.
All right, okay. So you assumed that, but you assumed that the landfill would be managed forever.
That's a good point. There is an inherent assumption there that the landfill will be managed forever.
But it was still not relevant, so it's okay
yeah.
to have that assumption.
Yeah.
Yeah, okay. Another detail, very much detail. You used the EDR 10, not 50. What was the reason? The availability of data, or why did you use that?
The availability of data was the main reason for that.
Okay, now I understand. The severity factor from USTOX, from PAF to PDF, do you think this holds in this case?
That is a good question. Unfortunately, my colleague was in charge of that bit of the modelling, so I'm not certain I'll be able to give you a proper answer to that.
Yeah, no, I'm just wondering because I thought this was made for the ED50, but even if, I think this is a very uncertain factor, another uncertainty, right? So, but as you say, it's a systematic uncertainty, so it doesn't really matter. Okay, maybe another more outlooking question. So your methodology, you applied it now to your case, but I think you can apply it to many, many more cases. Radiation is not only for bauxite residues, as you also say in your thesis, relevant, but also from other theses. Now you developed the impact assessment methodology, which is wonderful. What do you need? What do you expect now the LCI database developers to do?
Well, interestingly, the LCI developers already have emissions of nuclides like thorium-232 in their inventories that were previously going uncharacterized by the existing method. So that step in the process for at least some of the non-nuclides has already been done. It would be very useful if in all data sets where there is the potential release of these nuclides, they could be measured, assessed, and put into the database if possible. Additionally, the newer versions of EcoInvent have started to incorporate the idea of properties of the various products. So this can be stuff like carbon content or price in some cases. And because of the exposure route via nuclides incorporated into products, it would be very useful if these products could, in addition to these other properties, include properties describing the amount of radioactive nuclides which are contained within them. This is mainly relevant to construction products, but we also extended the method as part of paper 5 to deal with paving products as well. So for those types of products, it would be great if the database developers could have that information. Yeah.
You said, okay, the emissions are already included in the database, but for the construction products, I think they need, I don't really know when I understood you, they need to be still added, right?
Yeah, that's right.
Yeah.
Yeah, there's only certain processes that have these emissions already.
Yeah. I think it would be very, very relevant, especially to what you show here, no? That they are dominating by far, especially the nuclear fuel emissions.
Yes, yeah. Yeah, it's always scary seeing the ionizing radiation category in an LCA,
Yeah.
and then when you look into it, it's actually, because it's only from nuclear fuel, having a very, very small impact.
Yeah, it probably doesn't show the real potential. Mm-hmm. Let me switch a little bit to your software, which I think was very relevant to actually expand, and especially, I mean, I think you start from this open source development, which is, especially in the younger generation, I think, taking off, which is very nice. And you close an important gap, which is making it more usable, because right now it's really for experts, and that's it. But I'm still challenging a little bit whether you can, with your software, put lay people on it. So you said a little bit, the flow sheeting, this is a bottleneck. You said that also in your presentation. And I'm wondering, is it really the biggest bottleneck?
Perhaps not. Perhaps there is some training required to understand the life cycle perspective, particularly before you dive straight into using LCOps. But we have used it in a couple of master's courses, which is sort of an advanced layperson, because they've had some lectures on life cycle assessment. And so far, touch wood, it's gone okay, and was a lot quicker than teaching these master students how to use SEMA Pro, which would have taken a lot more time.
Okay.
So layperson might be pushing it, but it certainly seems to be more user-friendly than the other alternatives that are
okay, that is interesting. So you're saying, okay, if you have, let's say, advanced lay people, or that you kind of try to find which group had the quickest learning in terms of software abilities, the SEMA Pro guys and the new software guys, and you said, okay, they actually had a higher speed in learning it.
Yeah, well, there were different courses. So there's an LCA course where they're taught in far more detail how to do LCAs and are acquainted with SEMA Pro, because it's one of the most industrially relevant softwares to be able to use. But then there are other courses which were more about the concept of life cycle assessment, which were given to people in the biotech school, and there it wasn't necessary to teach them how to use a complex software like SEMA Pro, so we decided to use them as guinea pigs to test this new software on.
Okay. I think what you developed is extremely interesting also for the experts to speed up their work. I can imagine that this would be useful to anybody using LCA. And I was wondering, when we have students, very often they struggle with function unit and with the assignment of the right background processes. Does your program help a little bit in finding the right, let's say, background processes, or is this still something that everybody needs to learn?
That is, at the moment, still something that everyone needs to learn. Unfortunately, the search functionality for background processes in LCOps is quite limited. You need to know what you're looking for in order to be able to find it. But one of the great things about open source is that it's not just me that can add these functions. If there's anybody out there that's interested in doing it, they can always contribute that aspect as well. And so someone with more expertise in how to write better searches and how to push people in the right direction towards the processes, the background process that they need, could chip in with that bit of knowledge. LCOps is still continuing to be developed, and there's already a sort of mini community starting to build around it. And people are adding new stuff to it, which is really great to see. I'm really excited for the future.
So already now you see that the software that you developed is being developed also by other people?
Yeah, that's right.
Okay.
Yeah, that's right.
Yeah, that's nice.
Mainly people at ETH, but there are some people out there using it.
That's nice to hear. Let me get to another topic which I think was very interesting. So you had the prospective LCA in the end. I really liked your red flag approach, because I mean very often you don't have enough information, but this can actually really help the developers. So I think that's a great idea. You also said, okay, you mentioned the topic of technology development, which is an important one at that stage when you have such early stages. And you mentioned the upscaling issue. There's also a learning issue. By doing something, you just learn and get better. And I wasn't really sure how you dealt with both, actually, upscaling and the learning. I think I grasped a little bit of it. You said you didn't right away use the laboratory results, but you used similar. Is that how you did it? Similar existing large-scale processes to estimate, or how did you do it?
So the idea with the upscaling was to use the the lab scale data to inform a hypothetical version that could be seen at industrial scale. So rather than using a tube furnace or some kind of furnace that they would use in a lab for a very small amount of material, we spoke to people who were in the know, and it turns out there are rotary kilns and other types of kiln already available at alumina refineries. So Toby, my colleague in KU Leuven, came up with the idea of using existing infrastructure as the starting point for scaling up, because that would mean that there would be less of an investment for the people that would actually have to do this in the end, which is where the choice of rotary kiln came from. So the idea is that if you know the parameter which is from the experimental results, which is the temperature, then you can take, in this case, two versions of a rotary kiln, one that's being fired at a lower temperature, one that's being fired at a higher temperature, from the EcoInvent database, and use the energy required from there to extrapolate in between to figure out on a rough basis the amount of fuels that you require. So that's one example of how the scaling up works. But in more general terms, the idea is to come up with approximations or simulations of industrial processes that would still match the information that's being given to you from the lab scale results.
Okay, good. So you did not assess the lab scale at all. You went right away, you used the lab scale to inform a prediction of what could be your large scale process.
Yes, exactly.
Yeah. Okay, understand. Yeah. Let me come to your assessment. So you assessed in your first case study all the 12 midpoint indicators of the ILCD. In your second one, you went down to 4. Wasn't really clear why these 4, but maybe you can explain a little bit.
Sure. The main reason was that the patterns of results that I saw when I analysed the 12 impact categories in the second assessment were very similar. And so it seemed like a sensible approach, particularly as this paper was aimed at non-LCA experts, to reduce the number of impact categories down to 4 most representative of the different sort of axes of impact that could occur as part of the flow sheets. Okay.
In the first paper, you still sometimes say, okay, A is better than B in the majority of impact categories, and there I was stumbling a little bit and was like, yeah, but maybe the other ones are the more important ones. Did you look also at endpoint methods to cross-check a little bit? Or was it really just, midpoint in the strict sense?
This particular term was midpoint in the strict sense, partly because we're looking at contributions, but also there's slightly more uncertainty associated with the endpoint measures. Trying to compare something like the impact of climate change to the impact of toxicants on a human health basis is a bit problematic. So we stuck to the midpoint indicator.
So you said in the second paper, when you selected the 4, you kind of looked at the correlations between the impact categories and just took those out which went into the same direction, and then you took the 4 which were left and gave different results.
That's right.
Okay.
But if we were to apply this methodology for something else, you'd obviously start with all 12 and then see if the same thing holds, rather than simply using. I'm not recommending that those 4 impact categories be used for every type of this assessment. It was just it seemed like the best way to present the methodology, especially because, like you say, when you're faced with a chart with 12 different impact categories on it, can be a bit daunting to look at.
Yeah. Okay. Yeah. Because I was wondering, if you just look at the case itself, I would just off the top, I would say, okay, what is important is toxicity probably, and radiation, of course, and climate change. And I wasn't really sure why you included so many of the others.
Partly because the patterns were different. So toxicants correlated mainly with, I think, the climate change impact, but the eutrophication impact was completely uncorrelated to that. And so it was to provide more of an impact assessment in more directions, more axes, rather than sort of focusing everything down one sort of correlated route.
Yeah.
But in terms of the actual impact that as an endpoint impact or a normalized impact, there are other categories that potentially would be more important. But the idea is that for this sort of pre-hotspot screening that this red flags analysis represents. By solving one hotspot, you solve for one impact category, you solve the other ones with it, if that makes sense.
Yeah. No, and I think the red flag, this is a really great idea
Thank you
at that stage to really go in that direction and kind of communicate to the developers. This is a no-go. You need to find something else there. One aspect which I found very interesting is when you have your LCA results, then you come to different conclusions than actually you do with your case study because of the performance assessment later on, right? So if you just look at your LCA of your first study, you come to the conclusion as just use 100% BR and you're fine, right? That's the best option. But you also say, okay, this is not enough. We have this quality aspects. Do you have any ideas of how this quality performance aspects of the material can be integrated in a way so that in the LCA you already see this is actually not so much comparable, what you have compared there? This is a general thing which many people do and which everybody does. I mean, we also do this. It's a very difficult thing to include the quality aspects, but it seems to be essential because it's actually not the same.
Sure, I'm not sure I fully understand the question. So is this, so in the
quality, I mean with a performance assessment.
So
I mean you have
whether it can actually be used as a paving block, as an example.
Exactly. Whether it has the same performance as a pavement block or because this is, I think, your argument, right? Why not to use 100% BR, but why you go for the other versions?
I'm sorry,
If you, maybe I misunderstood, but in your paper, in your first case study paper, when you look at your LCA results, the option where you just have 100% BR always results to be the best option.
Yes, that's right.
But this is not the option you recommend.
No, exactly. Sorry, yes, I'm on the right, on the right page now. Yes, so the idea with that particular lab trial was to see if you could just use 100% BR to produce something that was usable. And as it turned out, it wasn't, and therefore it doesn't fulfill the functional unit, essentially. The functional unit for the study requires a 20-year lifetime, and in order to have a 20-year lifetime, it needs to achieve a certain compressive strength. And if it falls short of that compressive strength, then technically that functional unit hasn't been achieved. And so, yeah, perhaps including these items in the results where the functional unit wasn't technically achieved was a little bit disingenuous, but it served to show that you can sometimes go too far, I guess, with trying to reduce the environmental impact if you consequently reduce the function of the product you're trying to produce to something that is not going to be acceptable. In terms of how to incorporate that more broadly, at the red flag stage, it's difficult, I imagine, because the type of data, the type of stage you have to get to in the process in order to have enough data to talk about the characteristics of your products would probably push you to the point where you had enough data to do a streamlined LCA, and then you could set your functional unit like you did in the first one and find a way of producing your material that actually does serve the function it's meant to.
So what you're proposing is, okay, you have a functional unit, and that needs to be fulfilled, so you have a threshold approach. The materials that kind of meet these thresholds, they should be in, and the others should be out. And then you have different applications, maybe a high application and a low application, and those would include different options. Would there also be, and I don't know, I mean, I'm just throwing this in now, would there also be an option maybe to have a more continuous scale of quality characterization as an assessment, or would that be difficult?
That would be interesting. I'm just trying to think off the top of my head whether such a continuous quality scale would exist out there in industry. Sort of in the building products mindset at the moment, but as far as I remember, concrete products tend to have to reach a certain threshold to be classified as the next class.
True.
And so there are these various thresholds, rather than a more continuous scale where I guess purity of chemicals might offer one of these kind of continuous scales. But yeah, that'd be certainly something interesting to look at.
Yeah. Then it remains difficult. Because then you always have these steps for different applications, and yeah,
exactly.
So you focus a lot on bauxite materials, but actually the topic is much wider, and maybe you can elaborate a little bit on other tailing materials, other materials that you find for other metal products, for example, side products. Which ones do you see as promising also in terms of reusability?
Other industrial waste that could potentially be valorized? That's a good question. I know there's some work going on at KU Leuven looking not strictly at industrial waste, but in terms of batteries recycling and extracting rare earth element from those kinds of waste streams, which there could potentially be a lot of usefulness in. Electronic scrap is another potential source of valuable materials. I believe there's some work going on with zinc waste, potentially, which can be regenerated to produce fuel cells, but I'm reaching back into things
yes. There's an endless list, of course, if you go for all waste materials. I was more looking at metal production, because you were looking at aluminium now, side products of aluminium extraction and processing.
Unfortunately, my background isn't in metal production.
So you focus on bauxite.
I was thrown into bauxite residue, was as new to me at the start of my PhD as it may have been to some people here today.
So when do you see this coming for bauxite? So when do you see this coming into implementation?
It's a good question. In certain refineries, I can imagine it coming in very soon. Like I mentioned, there's one which thinks that they've got 20 years left before they have to make some dramatic changes to what they're doing in order to continue to operate. And so enthusiasm in that section of the industry is potentially very high. I can see in the next 5 to 10 years there being pilot equipment, at least, at this particular place. In other places where space isn't so much of an issue and environmental regulation isn't so much of an issue, potentially this could drag on and not be implemented fully. But once one refinery has shown that there's an economic benefit to valorizing bauxite residue, or as a very aspirational endpoint, treating the refinery not simply as a way of producing alumina, but extracting the maximum value out of the bauxite ore by tailoring the bioprocess, sort of bringing the bioprocess into the valorization flow sheet, so to speak. So you tailor the way that works in order to make the extraction of materials from the residues more amenable. If something like that were to occur, I imagine that would propagate pretty rapidly through the industry.
Okay, so you come from let's say from the side, we need a solution, and it will be there once we need the solution, and it becomes economical because there is no space left for some of these mines.
Yeah, there's certainly a lot.
On the technical side, do you think this is already? I mean, you could do it quite quickly. This is not a bottleneck that you need to develop these lab scale technologies.
From a technological perspective, some of the processes being developed by the Red Mud researchers have a lot of promise, particularly the inorganic polymers that very rapidly got going, which is why it provided good enough data for the LCAs. But also the guys looking at cements are making great strides. Reduction of iron, direct reduction of iron through electric arc furnace smelting is also looking quite promising. And some very high extraction rates are possible for the rare earth elements in scandium. Scandium in particular, which is very high-priced and valuable material, and so these look very exciting. Scaling up of those rare earth element and scandium processes might be a bit more difficult, and might be a bit more difficult to get economically viable at an early stage, and the volumes involved might be too low to have a major impact on the problem of bauxite residue in terms of running out of space. But some kind of combined process in which you're extracting valuable materials to tick the economics box and processing in bulk to tick the volume box, I think would be potentially a very interesting thing for the industry.
If you go now to the EPA, for example, and you consult the EPA, and what would you tell them to do? Because you said on the one hand, okay, if you already have a use for the secondary material, it's very difficult to enter into the market with a new process. On the other hand, you come to the conclusion the more sophisticated processes in the end, they are actually much better, right? If I understood you correctly.
Yeah, there's a level of sophistication at which it becomes beneficial, but over-sophistication may start to cause problems. So at the very end, we talk about combining the inorganic polymer and iron production, and that having an overall environmental benefit. At the moment, some of the more extractive technologies use such high-impacting reagents and recover this reagent at a sufficiently low level that if you did add that, it would then tip things back the other way in terms of the impact that is seen. So it's important as these technologies progress to keep on assessing to figure out exactly what level of sophistication and what level of valorisation is the optimum. But it's not as simple as saying the more you extract, the better it is, because there's the red side of the graph that you have to consider as well.
Mm-hmm. So what would you tell the minister?
More funding for more research, I guess.
I'm just wondering, because the simple versions of this you could implement probably right away, right? But
That's
the more
true.
sophisticated ones not. So,
yeah, I mean, joking aside, more funding to bring industry on board and scale up some of these to pilot scale would be probably the best use of these funds. Demonstrating to industry that this stuff isn't just a bunch of people in white coats messing around with bits of mud in a laboratory. And it's something that can be actually usefully applied at their refinery. And so it's worth investing in the infrastructure, worth spending that money on capital expenditure to do this. So yeah, and there's a project called Recover, which is a sort of a bauxite residue roadshow from what I've heard of it. They're creating a pilot plant for inorganic polymer production, which they can put into shipping containers, put on the back of a lorry and take it off to a alumina refinery and demonstrate what they can do. And those kinds of projects that grab the attention of industry and say, look, this is something that could actually save you a lot of environmental impact, a lot of money, is potentially the best way forward for these kinds of things.
Okay, great. So if you had another 5 years?
Yeah, another 5 years, I think the Red Mud guys could come up with something that would be very good.
Yeah. Will this be supported further, or is this now going to end? And
the training network is going to end, but I know that there are ongoing research projects, including stuff like the Recover project from people in the orbit of the Red Mud project that will continue into the future.
Yeah, great. Okay, thank you very much. I think I'm done with my questions.
Thank you very much.
For the ones that come here.
Thank you very much, Stephanie. So now it's time for the grading board, but I will give you some water.
Excellent.
Continue the discussion here. But keep seated and keep close to the microphone.
Yes.
Okay, let's see what the grading board has to ask you. Anyone who likes to start? Theodora? Yes, please.
I would like to start mostly because I'm in the beginning of your thesis. So my expertise is nuclear chemistry and hydrometallurgy. So basically, this is perfect combination of what you have done. And I was very happy to see that you included in the LCA analysis norm and T-norm, because many people are so happy to avoid that, especially industry. So that's a waste, it's a way, and nobody knows. Yeah. So I was very happy to read that you actually choose to have this approach. I have a question before I start with my other questions, because I don't want to kill you. Did you have the help from a nuclear chemist in this?
Yes, so Andrei Goranovsky was another PhD student who is at the University of Tartu, and he was the norm expert for the Red Mud projects, and he was a co-author on the framework paper and was a joint first author with me on the implementation paper. And his supervisor, Alan Tkachuk, also at the University of Tartu, helped on those papers.
Because before we start, I would like to, make sure that we have it right, because it's very important what you started to do. And you, as an LCA expert, you have to take into consideration the real dangers you have from this norm, radionuclides. So you mentioned that you have basically natural uranium, that you had to thorium and you had potassium. I was missing a little bit the radium, because radium barium is mostly, I mean, it's coming together with all the others, and it's also natural occurring.
Yes.
Um,
So
you had it in your first and second paper. I've seen that. So you had radium there, but you didn't mention in the beginning.
yes, that's right. So radium is assumed to be in secular equilibrium with uranium-238 because it's part of that decay chain. And so the assessment methods that deal with it and the inventories for radium, and so the numbers for radium and uranium-238 are assumed to be the same based on this assumption of secular equilibrium.
Because if you think about that, it's good, but you have to think that there you have a big uncertainty which you introduce in the model, because depending on the mineralization you might have actually radium which is not at equilibrium.
Yes, that's true.
So then this is actually the one which is producing a lot of radon. And it's the radon which later on in the construction sites is the one which is going to be the worst.
Yes.
Why?
Why is radon the worst?
Yeah.
Because it's a gas that can leach out into spaces and have an internal exposure through being inhaled.
Yeah. So basically you inhale radon, and what does that do inside?
Radon's an alpha emitter, so it would emit alpha particles into your lungs and potentially causes lung cancer.
So how is alpha compared to gamma?
So an alpha particle, if I remember this rightly, is a helium nucleus, and so it's a much heavier particle, and therefore does a lot more damage in a short distance of penetration, but it gets blocked very quickly. So gamma radiation, which is an electromagnetic wave, extends over a much broader spatial range, so you can be impacted by gamma emitters from the walls of your building, whereas the alpha particles would probably bump into some air on the way and not quite reach you. So were the radon to decay in your lung and release an alpha particle, that's potentially very damaging, but only from an internal dose. Is that correct?
Yeah, that's actually the most important part, because that's what it happens when you are in a building and you are in a closed room. You have radon, so you have a lot of alpha particles. What I was referring basically was that you have a high energetic particle with a very short range, and the discharge of that energy is 1 point. That means that basically it's rupturing any kind of bonds, any kind of chemical bonds. That means that it's rupturing water, carbon bonds, and so forth. So that means that it's basically total failure of tissue inside. So it can produce actually wounds which the body might not manage to heal in time, and then you start to get this promoter of cancer, you can say, for lung cancer. But I was thinking that gamma radiation is actually not as dangerous as alpha, because if you look from the shielding point of view, what can you say about gamma and alpha?
So gamma would require a lot more shielding than alpha, but
Can you stop gamma?
with a lot of lead you can stop gamma, but it does extend over quite a broad range.
You more or less almost cannot stop gamma. So basically what is happening with gamma radiation inside the house is passing through you, while while inside it's going to provoke a lot of damage. So then I was looking at the page 32, and I would suggest for the little human there in the house that yes, it gets gamma radiation, but I think that the most dangerous one you have to look after when you make the assessment would be the alpha radiation, because that's what it really provokes damage for the body.
Yes, definitely. So this is in the actual impact assessment method.
Yeah.
There are different dose conversion coefficients for gamma and alpha radiation from the radon. And so we use a radon exhalation model that accounts for the fact that when these nuclides are incorporated, when nuclides from the uranium-238 chain are incorporated into building materials, they will eventually exhale radon into the living spaces. And this radon obviously has a much higher dose conversion coefficient and therefore a much higher impact as a measure on the life cycle assessment method. The gamma radiation has a much lower dose conversion coefficient because, like you say, most of it passes through you, but if it does happen to hit something useful in a certain way and manage to cause disruption to DNA or something, you can have an effect of that. But yeah, the differential impacts between internal alpha dose and external gamma dose are accounted for in the dose conversion coefficients.
Yeah. So basically, I would say that when you look at the damage, and also when you have the workers, because I heard what you said that the gamma comes up and is shielded, and yeah, it's shielded to a certain point because you also have water in this kind of pools, and then it's really shielded. It's not as much. I think that the worst would be if these pools would be actually covered because you have a lot of radon coming out. So the exposure would be even worse. That was one. And then I was thinking, if you heard, now you have been for a while in Sweden, if you heard about a case in Sweden with building materials which actually had exactly that.
Is this the blue concrete?
Exactly.
Yeah.
So we should learn from history that we have had this problem before.
Yeah.
In that case, it was not the waste, it was alum shale, which was directly mixed into the composition, and then you have a lot of buildings which are built with this material. And do you know how they measure the content of radon in a house of these kind of buildings?
I don't know what kind of equipment they would use. I mean,
it's a very simple, extremely simple thing. Okay,
maybe
you so I can tell you that usually it's looking like a photographic film.
Okay.
And you have silver, which is in the composition of the film. And these alpha particles, when they are hitting this film, they are activating in their path about 30 atoms of silver. So actually you can measure each disintegration, how many disintegrations you have per minute, per hour, depends how long time you measure inside. And then it's very easy to assess the radon in a house with these kind of measurements. Of course, you need corrections. So that is something you can actually look, because here in Sweden there is a huge database about radon inside the houses and how they measure. It's a very cheap and reliable method. So that can be added to your work here, because as I say, you have a very good background, but I think you can add a little bit from at least from the Swedish experience.
Nice.
We have a bit.
That's a good suggestion.
Then I will not keep you that much over this. We can talk a bit later. But you also said in your thesis that the daughters are more dangerous than the initial nuclides you have, the natural ones. Do you remember which daughters? The decay daughters?
Sorry.
The decay daughters of uranium.
The decay daughter, so, well, the main decay daughter, the uranium chain is dangerous, would be radon, I would imagine.
Yeah, that's one of them.
Radium is more soluble than uranium, so that potentially would be another one.
Yeah. But I was also thinking that you get a lot of polonium.
Say again?
Polonium, yeah. So polonium is not only radioactively dangerous, but it's also, from the toxicity point of view, as metal, it is toxic. And it's very little you need to actually poison yourself with polonium without thinking about radioactivity. So, and after, when you have also the final decay of the radon, going down all the chain, you end up with lead. So that's also another thing which accumulates in bones and can be,
Yeah,
okay.
This impact category is just for the ionizing radiation part of that. And so the toxicity of polonium and lead is obviously very important, but would be accounted for in a different life cycle assessment impact category related to chemical toxicity.
I do agree actually with your saying that this part of the LCA should be separate from the one they use in the nuclear industry, because that's a totally different discussion. Here you have another type even if the effect is the same, but you have less radionuclides and less contribution from the rest when you have the nuclear fuel cycle, which is much more.
Yeah.
So I think that's a good approach, and it can be adjusted to fit different industries, because this is not the only industry which they get this type of residue.
Yeah.
And now I will finish with a fun fact. So do you know any other source of potassium-40?
Oh, there's plenty of good sources of potassium-40, yeah. Bananas are a very good source of potassium-40.
Yeah, and something which is much closer to you?
That's a good question. No?
So human muscles, we have a lot of potassium-40 in our muscles.
That's true, because yeah, sleeping next to someone provides you with a radiation dose.
Yeah, thank you very much.
Thank you.
Okay, thank you, James, and thank both of you for a nice discussion. What I got most of this thesis is that I think it's a very good demonstration of how you could use systems analysis for learning, as a learning tool for guiding future research. I think that is the contribution I'm most interested in. So therefore I would like to ask you kind of a general question, because you've been working now with LCA for a while, and you have been working on emerging concepts or technologies. So I would like to hear from you, what are the main different challenges that you see with using these tools particularly on emerging technologies?
So the main challenge is in relation to the data that's available, but the data availability comes with its own particular paradox, in that the more you know about how you're going to do a process, the less scope there is for change. And so by the time you've got enough data to do a good LCA and get some very accurate results on the potential environmental impacts of your process, you're so far down the design process that there's very little scope for changing what you're doing. And so the major challenge for me, from my perspective, I think, is trying to incorporate LCA into design processes as soon as possible, so that there's still some residual leeway in the way that the design can be significantly altered if you're coming up with major hotspots at a very early stage.
Yeah. There are also, there is one thing which I was thinking about. There are so many options of how you could deal with this. How could you handle that from an LCA perspective or a system analysis perspective? Because now in your thesis you're looking at one or two scenarios, or a couple of scenarios, but there are many ways of dealing with bauxite. So what do you think could be the role of LCA in guiding research on which of those combinations of different technologies that you should put your money in?
It's a good question. I mean, I'd hope that the red flags analysis contributes somewhat towards this. The way that it functions as part of that the paper that it's in is that a gigantic flow sheet containing lots of different pathways all linked together was put together with the help of the other researchers in the RedMod project, and then each of the different inputs to each of these different pathways was allocated to a particular output depending on where it occurred in this particular flow sheet. And so the red flags that we see in that assessment do broadly give us an inference onto what are the most important materials to either reduce or avoid when you're running these processes. But it's probably not, like you say, enough to point you immediately in the right direction, given the number of options that are available out there. So from that perspective, I think repeated analysis through the design process, sort of validating as you go along, and as you start to, from a technological point of view, focus in on a process that works, is an important aspect of this. Because yeah, from the other researchers' point of view, making sure their process works and that they hit their milestones for 99% extraction of scandium is the thing that they're focusing on. And so pointing the researchers down a dead end and saying, don't use ionic liquids because they're too bad for the environment, and leaving them with fewer tools at their disposal is potentially not the best thing to do. So it's a bit of give and take between providing useful early information and closing off potentially important technological routes for these kinds of valorization. That a balance needs to be struck between.
Yeah, and I was a little bit surprised. I like your work very much, but I was a bit surprised that you were into this discussion a bit before, but you have not really dealt with uncertainties to any large extent. And for me, dealing with uncertainty and sensitivity would be a very key content of any kind of prospective LCA. So I was thinking about why have you not dealt with that, and what is the risks or pitfalls of not including neither scenario or parameter uncertainties, or modeling uncertainties for that sake?
In the case studies?
Yeah.
It's a good point. Primarily the reason for excluding uncertainty was because there's already so much uncertainty inherent in the assumptions that trying to add in extra elements of uncertainty in terms of a quantitative analysis wouldn't serve any useful function. These are already quite high-level assessments, and the kinds of inferences you can take from them are basically this accounts for 80% of the impact, so we're probably pretty confident in saying that that's a hotspot environmental impact, but this only accounts for 2%, so we're pretty confident that we can say that this is not a hotspot of environmental impact. And knowing, unless the uncertainty is vast around those two extremes, then there's probably not a lot that uncertainty could add at this level of inference, because we're not really comparing anything in a particularly major way. Because we're looking at the hotspots of a single system. There's no way that error bars can cross, really. You can say the closest you might get is to have two things that are making a similar contribution, and you would be uncertain about this one's 21%, this one's 24%, which one is actually providing a higher contribution. But the main inference you can take from that is we have two different things, each contributing roughly 20% of impact to this particular impact category. So both of them might be important, unless the remaining 60% is taken up by one single thing, in which case that would be top of your list for looking at making improvements.
I think that if you would include parameter uncertainties, I mean in terms of what could be the minimum and maximum values of different resource inputs and efficiencies, you would have a lot of overlap between these different processes.
True, yeah, true. If you're trying to make
instead of having them separate.
Yes, you're right.
I was thinking about, for instance, if you look at, is it figure 18 on page something 57? You have done this, it's the last article, I think, where you look at this integrated processing scheme of using bauxite residue as both for iron recovery and for using it as paver blocks. One thing you could question here is, for instance, okay, what could vary here? What could make these results vary a lot?
Yep.
And then you could think about it in different ways. You can think about it upstream, saying that, okay, what about different feed materials here?
Yes.
I don't know how bauxite residue is, but I assume it could vary a lot.
It can vary a lot.
Even when it comes to iron content. And then I would like to know that in that kind of study that, okay, you can get a lot of benefits from recovering iron if you have exactly this amount of this bauxite.
Yes.
But if you have bauxite from this region or there, you will have too low concentrations, so it will not make a difference.
Yes.
For instance.
Yeah, that's correct. Yeah.
That's what I mean by using uncertainties.
Okay, of course.
I guess the same is also when you talk about iron recovery and primary iron production.
Yes.
The resource that you need to do that varies also depending on where this iron is produced.
Exactly, yeah.
Which is another of that kind of uncertainties. Okay, well, enough about that. One more question was about this. I really like your idea of having this LCA for guiding a particular process, as you do in paper 5, or guiding the further development. But I was thinking about what are the risks or limitations of having such a narrow perspective on process development, looking into one process in depth without really considering how it interrelates with upstream and downstream processes?
In what sense?
From an environmental point of view.
So, well, the assumption in this case is that this is the bauxite residue, which is the major upstream process of this, is a waste of the aluminium sector, and using the cut-off approach, this enters the system burden-free. So in that respect, the only upstream impacts taken into account are the production of the energy and materials that you require in the valorisation process. And in terms of the downstream processes, the use phase and the disposal phase were included in the assessment. The disposal phase had a very low impact in the vast majority, if not all, of the impact categories assessed. So if we look back at, I'll just get the figure up. The orange ring here, the orange ring in the second ring outwards. Does this show up? Yep. This is the block itself, and then the disposal phase is this tiny sliver here. So that's the downstream impact, and so we're pretty confident that given that we're using a burden-free input in terms of bauxite residue under this methodological choice, and the small contribution made by the downstream impacts, that focusing on this particular process is not too much of a risk.
No. But you don't get any grip when you do this, of course, about the relative importance of these things. I mean, you see a relative difference between the different mixing agents and that kind of things, but you don't get a grip about, is this important at all in terms of the full value chain? Or is all the benefits or impact coming downstream or upstream? How important is this process for that environmental impact? If you want to produce paving blocks, how important is the process impact? You don't get anything about avoided impacts here in this study, right?
No, not in this study. There's nothing about the avoided impacts.
So in which order should you do this kind of assessment? If you would do something, would you start with paper 6 and then go for paper 5, or will you start with paper 5 and then go for paper 6?
You start with paper 6, then go
yes.
for paper 5.
Good.
So yeah, it's important to take that into account. Yeah, the reason that they're in that order is because it's going from simple to complex rather than complex to simple in terms of the valorization routes.
Finally, I was thinking about this. I also like this size of the price thing that you have, because there you could already there start to inform about how you could integrate different processes. Mm-hmm. But I was thinking about, why did you use upper limit values here?
Because lower limit values are 0, and upper limit values seem to be the most sensible approach to take. People may know roughly what proportion of these materials they're able to extract, but the milestones for the REDMA project tend to be in the upper 90s, in the 99% range. So 100 seemed like a reasonable end of the scale to go for, and it sort of provides an impetus to make your process as efficient as possible, because the more efficient your process is, the closer you'll be to the kinds of inferences you can make using this 100% size of the prize assessment.
Yeah, I think 100% is okay, but I was thinking about also here that why not present these figures as ranges? I mean, if your idea is to guide future research and how to integrate different processes, so what could be the potential of recovery from bauxite? Why not use ranges? I mean, the minimum, maximum values of carbon dioxide savings from recovering aluminum, iron, or whatever.
It's certainly a good idea, but like I said, the minimum when you don't know anything is 0, and so the range is meaningless. If you do have more information, obviously, if you know that the minimum process efficiency that you're going to consider for taking this technology forward is 85%, then you could have a range between 85 and 100%. But the starting point for this assessment was the idea that there's literally nothing known about this, and we know roughly what stuff we're going to use, but we'd have absolutely no numbers to work from in order to come up with these kinds of assessments.
No, but I guess, I mean, your idea here is that you have 100% recovery, but then you have a certain amount of savings per ton of materials that recover, which also varies a lot.
Yes.
Depending on where you are and so forth.
Yeah.
that's what I meant. I understand that you don't have any figures about exact recovery efficiencies because that is
yeah. No, you're right. It's
tricky
just,
to get.
this is just the global average in this table as opposed to the ranges. But yeah, I mean, the more information you have, the more information you can use in this assessment. So if you knew that you were going to be displacing local building products in Greece, then you would use the impact of local building products in Greece for the size of the prize.
And I think that is important for emerging concepts because you don't know where these processes will be established.
Yes.
Exactly.
Yeah.
And you don't know for which materials or when.
Yes.
So that are also important aspects to include, I think. Yeah. Okay. Thank you very much.
Thank you very much. Thank you.
Hi. I'm lucky last here. Thanks for a great show and a very interesting thesis. Like our opponent, I was excited by the breadth of stuff in it. So I'm going to ask a couple of questions that have almost no relationship to each other. One thing that struck me reading this was the question about modes of life cycle assessment. And I'm not really sure where you've landed on that topic. So maybe we can just clarify that a little bit. You say on page 22 of the thesis that you've taken that attributional approach. Would you like to comment on that?
Sure. There is a lot of discussion around attributional versus consequential approaches to life cycle assessment. My personal view is that the arguments that take place in the literature represent sort of a false dichotomy, and that the most useful type of life cycle assessment is the type of life cycle assessment that helps you answer the specific question that you have in that particular study. In the particular studies in this thesis, the right approach was more at the attributional end of the spectrum, but it included some aspects of consequential LCA, including system expansion and including avoided products, because that was a useful way to do these analyses.
So would you say that paper 5 is an attributional CA, or you would rather say it's consequential because you've given it the title anticipatory?
Yes.
Which is perhaps another kind.
There is. Well, there's multiple types of LCA.
Yes.
But anticipatory probably I wouldn't put on the same spectrum as attributional and consequential. Attributional and consequential for me tend to be more around the modelling assumptions that are made throughout the background system and the foreground system, whereas the anticipatory side of this is more strictly related to the foreground system of the LCA.
Okay. I mean, my feeling from reading Wender's paper was that he seems to think that the anticipatory LCA has to do with essentially prospective information being used in the LCA, not necessarily forward or background, but also the incorporation of social science perspectives into the scoping, selection of the functional unit, and the impact categories and so forth. And I don't think you've really focused on that kind of thing. And perhaps it's very difficult when you're dealing with technologies that don't actually have natural stakeholders in the community. There may be companies that want them to be built or something. But
yeah, that perspective on anticipatory LCA is certainly broader than the focus of these papers. When there's a specific idea and a specific company in a specific location where this might be put into practice. It was more about anticipatory in the sense that this technology doesn't yet exist, but we can estimate what it might look like when it does exist, rather than that more broader perspective.
See, I think it could have been more traditional and just called that a prospective LCA then.
Yes, quite probably.
Okay. On a completely other topic, I like that you've been experimental with some of the ways you've presented data. We talked about these threshold numbers you produced in, was it paper 5, or I think it was 6, which I think is a useful way to do things. I struggle a bit with this kind of figure.
Yep.
Tell me, why is that better than a stacked bar chart?
It's because a stacked bar chart will tell you so there might be a picture of a stacked bar chart somewhere I can show you. There you go. So a stacked bar chart will tell you that when you make a cup of tea, water is important. I don't know what is important. Tea leaves are important and milk is important, but you don't know where in the process your tea leaves and your milk are coming in. A stack bar chart, if you had electricity at various places in your supply chain, which would be a better example, a stack bar chart may just have a single block which refers to electricity, and if you were to split this electricity up into the different places it occurs, you'd have a colour for electricity from process A, a colour for electricity from process B, and so on and so forth.
Not necessarily. It could be the blue bars across the bottom of your stack bar chart there. If those are all the electricity in, let's say, 3 different processes, not necessarily the titles you put on there, but you could have different processes left to right, or different processes top to bottom in terms of the unit operations. And then you could have where the background processes fit into them also, either as columns or segments of columns. So
yeah, I mean, it's another way of doing it. Another way that you could do it is use something called a tree map, which is a more square approach to identifying where it's more about the hierarchical structure of the information, which is why this diagram is used, as opposed to presenting hierarchy on a bar chart seems to me to be more difficult than trying to present it in something more like a tree diagram or one of these hotspot diagrams.
These hotspot diagrams, are they all in your thesis? You've got them in various places from the front end through a couple of papers also. Are they all produced with the same software, or you've drawn them by hand? Or
they're all produced with the LCOP software, yeah.
Yeah. Because one of the things I noticed looking at them was that the thickness of the rings seems to vary or not vary by a larger or smaller amount. It seems to me, for example, if you looked at you had the picture we started with there from page 50 of your thesis, this guy. Those 3 down the bottom there, we have the same radius or difference in radius at the 3 levels. Or there's several levels there. You've got the orange, and then what have we got? 1, 2, 3, 4. Okay. Whereas the picture you just flicked from page 42, the thickness varies. And this, in a way, is my key uncomfortability with it. If you go back to the other one, page 50, the area of a segment in, well, let's say the total area of segment 4. Is going to be 50% larger than what you've got in segment 2. So if you compare material, compare the area of those things, and you're thinking about the scale of the impact, I think you get misled if you jump a level. Whereas the outer rings ought to be diminishingly thick if you're going to represent equal areas for equal impacts.
Yes, if you wanted to represent equal impacts for equal areas, that would be the case. But here, arc angle is the measure rather than area.
But I think when a person looks at a diagram like that, area is size, is impact. And so that's why I think it's a little misleading.
Yep, that's true. There are options within LCOP to decrease the size of the outer rings. This was mainly because the further you get back into the process, the smaller the contributions to the total are, and so they're diminishing in importance. But it could be rewritten to make it so that the area more closely relates to the impact that you see.
Yeah.
The reason I didn't use area is because when you do have, like you say, multiple levels and the size is diminishing so that the area of the outer ring matches the area of the inner ring, you start to lose sight of these rings as they become basically lines at the edges of a larger chart. And so, although you're right that if you were to assume that it was area that was the measure here, it would be a distorted view. These go with arc angle. Yeah.
You need to have a thing that someone can interpret instinctively. The whole point of a visual representation is that I can just say, bang, there's the result. So anyway,
the main idea with this was just to replace the scourge of LCA master's thesis reports all over the world, which is the copy and paste from SEMA Pro of the bifurcating Sankey diagram to show the various hotspots going through.
Yeah.
And so, as long as it's a step up on that, then that's the main aim.
Try Garby. No, I move on. All right. I had one other question I wanted to ask you, which is, I was kind of curious when I looked at the pie chart on what's in the bauxite waste, bauxite residuals early on there somewhere. And I thought about the amount of iron in that. You've got 41% hematite, which is about 70% iron. That's similar to current domestic Chinese ore, and it's better than current domestic American iron ore.
Yep.
So it's puzzling that recovery processes are as rare, as you say, less than 3% of the waste is being recovered.
You're absolutely right. In fact, Carl Josef Bayer, the guy who invented the bioprocess, pointed out that the residue would potentially be useful as a secondary source of iron.
Yeah.
So it is puzzling that it hasn't been taken up more broadly. I think part of the issue arises from handling issues of the waste associated with its highly caustic nature. So the residual sodium hydroxide that's left in there makes it difficult to handle, and also makes putting it into reactors difficult, because it will attack the reactors potentially that you're using. And the additional economic and technological burden of neutralizing it before you use it as an iron ore may have represented a barrier in the past. But iron extraction is something that has been seriously looked at for a very long time. There's been a pilot scale iron extraction process that was put in place at Aluminium of Greece. It was called mud to metal, where they not only produced iron ore, but the slag they then turned into rock wool, so insulation, as a sort of initial step into the idea of 100% zero waste valorisation of this residue. But I'm just as puzzled as you are to why it hasn't taken off more broadly industrially.
Okay, that's for me.
We wanted to comment. Yeah, I just wanted to comment your question. Maybe it's also good for you. Can you hear me? So one of the reasons they don't really want to do too much recycling of this type of waste is that they will concentrate then the norm. They will concentrate uranium. That means that at that point they will have a concentrated stream of uranium which will go under the jurisdiction of Euratom, because at that point it's already nuclear waste. So that's one of the things. They don't want to deal with the rest of the material, because then they have to declare and to probably renew a lot of, I don't know, papers for this type of process. So that could be one of the problems, because then will cost a lot of money, aside the fact that it's a chemical burden.
That's a great explanation.
Were you ready? You're happy? Okay. Thank you very much for interesting questions. So now I open for the rest of you. If there are any other questions you'd like to pose to James, or comments in relation to the discussion you have been hearing here? No arms, no hands. Yes, Nicholas. I will give you the microphone here.
Yes, I was just wondering if there's anything, or if you're going to keep working with LCOP to develop it further, or if anyone else is going to use it in a broader sense, or was it mostly developed just for the specific project? Do you have further plans for it?
Yes, in short, when I have the time, I'm continuing to develop LCOPs, and some new functions have been added to it since the published version. So you can now do mass flow diagrams with it, and the waterfall chart that you saw in the figures for paper 6, you can now natively create within LCOPs, which is new from the published version. And there's a few people out there in the wider world, some at ETH. There's a guy who's at TUM in Munich that have come across LCOPs and are active open source software developers, and they've been helping contribute to it as well. So the plan is that LCOPs will live on beyond this thesis and hopefully be developed either by me or in a collaborative sense into something that can be really useful.
Thank you. So, anyone else when I'm up here? Okay, and and I see you all. Okay, final call. So, if not, I thank you very much, James, and also you, Stephanie, and the grading committee, and everybody for coming here today. So, as I said, what happens now is that the grading committee will gather and discuss the examination of your thesis. And all of you who are here are very welcome to come along up to our department. We will meet in at the street Teknikringen 10B. And if you don't know where it is, you can talk to me or follow me. And we will meet in the entrance floor in the lounge there. There will be some coffee, refreshments, snacks probably, until we wait for the grading committee with their answer. Okay, thank you all.